Hello, today we'll do the derivation for electric potential any point because of an electric dipole. This derivation is a very important derivation. So we'll take minus q plus q, point A, point B. The distance between these two is 2a. Now we'll consider a point P, observation point P. Consider a point P at a distance r, making an angle theta. Consider the point P somewhere here. We'll take it from the center of the dipole. This is distance r, and this is angle theta. Now we'll extend this line backwards. Now we'll do some construction, that is, we'll draw AN perpendicular to PO. Consider this point as O. So we have extended PO and we have drawn a perpendicular AN on PO. Similarly, draw a perpendicular BM on PO like this. So we'll mention the construction work. So draw AN perpendicular to PO and BM perpendicular to PO. Now, as we can see, PA is approximately equal to PN. That is this. PA is here, is approximately equal to PN, which we can write as PO plus ON, PO plus ON, and we can write it as we know PO is R, so R plus ON. ON is this. If this is the angle theta, then this is also angle theta. So we can write ON as A cos theta, because ON upon A is equal to cos theta. Cos theta is equals to ON upon A. That is this distance. Similarly, we can see that PB is approximately equals to PM. That PB PB is approximately equal to PM. That is this. We have to mark PM here. So we'll write PM as PO minus OM, PO minus OM, and we know PO is R and OM, that is here. Actually the figure shifted, so theta is this. So OM can be written as A cos theta, because OM upon A is equals to cos theta. So now the potential difference due to the charge at A, that is VA, will be equal to minus KQ upon PA, and similarly for VB will be equals to minus KQ upon PB, as we can see from here. PA because the distance between minus Q and the charge at P, and PB because the distance between plus Q and the charge at P. So minus KQ, and we have found out PA to be R plus A cos theta, and VB is equals to minus KQ upon R minus A cos theta. So to find the net electric potential, we add them, VA plus VB. We take KQ common to avoid steps of calculation. We write 1 upon R minus A cos theta minus 1 upon R plus A cos theta. We take the LCM. KQ, it's R plus A cos theta minus R plus A cos theta, and in the denominator we get R square minus A square cos square theta. So KQ upon A, R and R gets cancelled. So we are left with 2A cos theta upon R square minus A square cos square theta. And as we have done in the previous derivations, we write it as V is equals to K cos theta into 2A into Q, R square minus A square cos square theta, and we know that 2A into Q is the dipole moment P. So the electric potential becomes K P cos theta upon R square minus A square cos square theta. This is the electric potential due to dipole at any point. P is the potential difference, theta is the angle it makes, R is the distance, and A we already know. So we have some special cases. The first one is if P lies outside, if P lies on the axial line. So we'll derive the derivation we have done before. So then theta becomes 0. If this is minus Q plus Q, we had P here. But if the P was here, then the angle it will make with the dipole will be equal to 0. So we get V is equals to Kp upon R square. This we derived for the derivation when we did electric potential on the axial line. And if P lies on the equatorial line, then minus Q plus Q, and P is here. So it makes an angle 90 with the dipole. So we get V is equals to Kp cos 90 upon R square minus A square cos 90, which is equals to 0, which is also what we derived. So basically the two cases, the two derivations which we did before are conclusions for this one. These are basically conclusions from this derivation. Thank you, and I'll see you in the next video.